Any questions on the flow demand estimation stuff that I handed back? By Friday, you need to have your first attempt at sizing the pipes completed. And the submission for that is 2 printed maps with annotations showing the pipe diameter, the flow rates, the pressures at the junction, and so on. I've got a question about what elevations should use for the junctions, and it's okay to use just the ground elevation for the junction, or if you'd like, you can assume that each of the junctions is buried the same depth underneath the surface. And so maybe if you find the elevation of each of the junctions, then you could say that the junction itself is buried 2 meters lower than that. You know, either approach is fine. But I have sent out an email that has the installation instructions for WaterGems if you want to put it on your own PC, including the web address you need to download the software and the school code that you should use and so on. Let me know if you've got any questions related to that. The homework that's due on Monday the 11th, that is 5 problems that are all solving essentially the same equation, Manning's equation. Just, it's important enough that you need to get a lot of practice solving that, and we're going to take a couple of examples from Manning's equation today. Any schedule or announcement questions before we move into the lecture? Just to step back and take a reminding look at the cross-section for open channel flow. Remember that when water is flowing downhill under normal conditions, meaning steady, uniform flow, the energy grade line, the hydraulic grade line, and the channel slope are all equal. That was one of the questions that the other section had on their quiz, was what 3 slopes are equal to each other under steady, uniform flow. And so those 3 slopes is the channel bottom, the water surface, and the energy grade line. So under steady, uniform conditions, those are parallel. And what you'll notice is that the energy loss is equal to the slope channel, the elevation change due to the channel slope. So equilibrium is when if you were to extend a horizontal line from this location 1, then the amount of energy loss would be the horizontal line down to the energy grade line. That elevation difference, delta Z, would be the same as the elevation difference between the horizontal line here going up to the channel. And so that's one of the ways that you know if conditions are steady is if the head loss is a function of the channel slope. So one of the relationships you'll use in the homework assignment is the relationship between shear stress and energy grade line slope. And I've noted that you need that for problem 1116 because it essentially tells you that there's a certain level of shear stress allowable in a channel. And when you know how much shear stress can be tolerated by a certain soil, then that allows you to know what the slope of the energy grade line should be. And then from that, you can substitute it into Manning's equation and find any of the corresponding hydraulic parameters, like the maximum flow rate, the maximum velocity, what depth corresponds to those conditions, and so on. Manning's equation was preceded by the Chezy equation. And we've talked about that before, but what we haven't mentioned is that sometimes there are tables of Chezy roughness factors, and you can convert between the Chezy roughness factor and Manning's equation using this formula here, the formula that has both C and N. Sometimes there are tables that will classify materials that are kind of obscure, and maybe the only reference you find for it is the Chezy C value. And so you can convert between the 2 using that formula. The reason why Manning's equation was adopted is simply that it provided better fit to observed data. It's an empirical equation. It's not necessarily fundamentally correct, and you'll notice if you compare the units between the right-hand side and the left-hand side that it's not dimensionally homogeneous, meaning that if you have hydraulic radius, which is units of meters, and you take that to the 2/3 power, slope is unitless. And so just by taking meters to the 2/3 power, you don't necessarily get velocity, which would be meters per second. And so it's not dimensionally homogeneous, and that's one of the hints that it's an empirical equation where there's been some curve fitting done. And that's the purpose of the n value, is The N value is a resistance parameter that makes observations in the field match into the empirical equation. This is the table of N values that's provided in your text, and we've seen a couple of other ones and talked about how the range of conditions that you may see in the field dictates which Manning's N value you use. And so in the case of natural earth, good condition could be between 0.018 and 0.02. The interesting thing is that you can also estimate the N value depending on the diameter of the material that's used in bedding. And the Strickler equation, which is shown here, is a formula that relates the diameter of gravel to the roughness value N. This is for a relatively smooth pea gravel that would be found in the bottom of a channel. And we'll just do a brief example to illustrate how this works. If you have gravel that is 0.5 inches in diameter and would like to calculate the N value from that, you simply d sub m of 0.5 inches divided by 12 inches per feet gives you 0.04167 feet in diameter. And if we substitute that into the Strickler equation, then this term is 0.589. So the N value is 0.020. Okay, so that would be for a relatively standard half-inch diameter circular stone particle. And the interesting thing is that if you compare that N value of 0.02 to the table, there's a lot of other materials that aren't necessarily gravel-lined channels that will have a similar roughness value. So, for example, riveted steel may be 0.02, and so you'd have to think, what is it about riveted steel? You'd think steel is more smooth than gravel, but perhaps it's the effect of the rivets themselves imparting some resistance similar to the way that gravel might, or even for just a natural earth channel in good condition, and so that would be bare soil. Even though the individual sand grains and the soil grains are much smaller than the diameter of a piece of gravel, a half-inch diameter piece of gravel, the same N value of 0.02 for natural earth, good condition, could be for a channel made out of that natural earth soil. And so it's not just always about the material that it's made of, but it sometimes has to do with the surface of the bottom of the channel. So there could be irregularities in the natural earth that are larger than the individual soil drains. It could be that there are clods of dirt. It could be that there's rocks poking out of the natural earth. Just essentially how smooth the channel is, or how smooth the channel typically is. And let me just jump really quickly to this picture because it addresses the issue that we're talking about. You know, this would be, I think it's primarily clay and stone. And so the individual grains of stone, you know, it may have an equivalent sand roughness that's very small, but you can see that there's that surface more broadly is very irregular. And so there's going to be a roughness there that depends on more than just at the molecular level what it's made out of, but it has to do also with how jagged the soil is. And so we'll come back to this picture and talk about some additional things related to it, but I just wanted to point out that even for a material that you maybe would consider smooth by itself, you know, like some clay, when you make an entire channel out of it, just the way that it collapses and breaks apart is going to have a different resistance than the individual grains that it's made out of. All right, so like I mentioned, a big part of this next assignment is just solving Manning's equation to find the normal depth. So Manning's equation we can express both in terms of SI units or British gravitational units, the difference being this factor of 1.49. If we rearrange for what we typically will be given, like a flow rate, an N value, which characterizes the roughness, a channel slope S. What's now left on the left-hand side are the geometric parameters for the channel that will have depth, Y, as an unknown. So if we move everything that's a numerical parameter to the right-hand side, then what's on the left-hand side is some unknown depth Y. And you can put formulas for the area, the wetted perimeter from table 10.1 in your book. If you're trying to find the depth, you can put all of these formulas in to the formula for A and hydraulic radius in order to solve for the unknown depth Y. And so we'll take a look at an example of that with this equation. We've got a channel that's 3.5 meters wide. Side slopes are 2.5 to 1. And we're trying to accommodate a flow rate of 29 cubic meters per second. To solve it just by trial and error, what we'll want to do is move the Q and the slope and the M to the right-hand side. So let's first of all just make note of the fact that it's 29 cubic meters per second. The slope is 0.001. The end value is 0.014. The bottom width, 3.5 meters. T, which is the side slope, horizontal component, 2.5. And the depth Y is the unknown. All right, so the area factor, if we go to the table, is going to be 3.5 plus 2.5 Y times Y. And that's for the 3.5B and the T. The wetted perimeter we can calculate once we know this factor W. And in the table it says that W is 1 plus T squared to the 0.5 power. And so for us it is 1 plus 2.5 squared to the 1/2 power. So W is 2.693. Okay, so for the wetted perimeter then will be 3.5 plus 2Y times the W, 2.693, and that gives us the wetted perimeter. One of the substitutions that I sometimes use, area times the hydraulic radius to the 2/3 power. There will be times where it's very convenient for us, instead of writing it like that, to instead write it in terms of the area to the 5/3 power and wetted perimeter to the 2/3 power. Okay, so if we do that, it's 3.5 times Y plus 2.5 Y squared to the 5/3 power, 3.5 plus 5.385 Y to the 2/3 power. And that's just simply multiplying the 2Y by that factor. And we're taking everything to the 2/3 power. Okay, that's going to be equal to the N value, 0.014, 29 cubic meters per second, and the square root of the slope. Okay, the right-hand side of that equation is 12.839. And so really what we need to do is find what Y value is equal to 12.839. What I'd like you to do is, with your calculator, hopefully you've got an equation solving capacity on the calculator that you use, try and find Y. I think on the Casio calculators, if that's what you're using, you have to, when you type in an equation, give it an initial guess in order for it to converge on a solution. And this is going to have multiple roots, one of which is negative. And so the initial guess that you maybe would start with is say, well, maybe the depth is 0.5 is your initial guess. All right, so try that out. See if you can find y. What I'll do is show you a little demonstration on writing Manning's equation in terms of variables rather than specific numbers, because it can be convenient to have it written in terms of variables if you want to solve it later on. So this is a calculator that I sometimes use that has the ability, it's got a built-in numerical solver, and if you say that you want to write an equation, there's this thing called the equation writer, and the advantage of having it in this way is that you can actually see the equation without too many parentheses. It actually builds it the way you'd see it. So let me show you what I mean. Okay, so Q is equal to, we put in some parentheses here. Okay, it is going to be B plus T times Y. And that's times Y. And that is to the 5/3 power. That is times S to the 1/2 power. So you can sort of get a sense for the fact that it's a lot easier to write the equation when you've got an equation writing mode that stacks it visually the way that you write the equation naturally. And a lot of calculators have the same functionality. It's not just the HP ones. Okay, now B plus 2 times Y times 1 plus T squared and that's to the 1/2 power, and all of this is to the 2/3 power. Okay, and now the nice thing about this is that we can put in any number we want for any of these variables, and it'll solve for the one that hasn't been entered. And this example that we've just worked, we have an n value of 0.014, right? Is that the conditions here? Okay. Bottom width of 3.5, and the slope 0.001. The t value has to do with the side slopes, and then the flow rate, we'll change that back to the 29. Oops, 29. And then the thing that we don't know is the depth, and so you just click solve, and it'll instantly find the depth, 1.66. And so we could change any parameter. If we were doing design and we wanted to know what, if it's this channel geometry and we saw a depth of 2, then what would be the flow rate that corresponds to a depth of 2? And it can solve the parameter that's highlighted, and you just click solve. Or if you had 40 that you knew, then you wanted the depth to only be 1.75, then how wide should the channel be? You can say solve for B. And then we'll say, my battery just ran out. It was giving me the low battery warning earlier, but I think it really meant business at this point. You get the idea, though. You write the equation in terms of symbols, and then you can substitute any value you'd like for the symbols that you're using. So you'll get plenty of practice on this next homework assignment having to do with Manning's equation and solving for the unknown flow depth. Besides making the point that this channel shows the irregularity of a surface depending on more than just the material that it's made out of. This also shows the effect of excessively high scour velocities. And oftentimes because of urbanization, or the process of people putting in a subdivision where it used to be a forest, or putting in a shopping center where it used to be a grassy meadow, any sort of natural cover is going to be allowing infiltration of rainwater into the soil. But then when you pave over that with concrete or asphalt, or you put a roof that's not permeable, you're increasing the amount of impervious area, and that'll increase the runoff flows that make their way through streams. And so this is one of the side effects of human development, is that always the streams around us have a lot higher flow rates going to them during storms than originally before construction was put into place. And so the consequence of that is that the flow depths will be deeper than they would have ordinarily been. And because the flow depths are deeper, the velocities are higher, and then the scour will remove and break apart the surface because it may not be naturally resistant to the types of velocities that happen after urbanization. And this is an illustration of a channel that's been quite badly damaged because of excessive scour. And you see this all throughout West Virginia. People will build their homes next to channels, and the channels will erode and scour, and they're just simply not stable because the flow rates going through them are higher than they ordinarily would have been. And one can relate the shear stress to maximum velocities that should be allowed. And you can do a geotechnical analysis of a soil or other material to find the maximum allowable shear stress, and that will correspond for a certain slope that the channel is going to be laid out on. What you'd end up finding is a hydraulic radius, and it's just not a physical parameter that's meaningful at all, but it's a representation of the ratio of the shear stress to the slope. We'll do an example of that here in a moment, but once you calculate the hydraulic radius that is dependent on the shear stress and the slope, it can go into the Mannings equation, and the unknown here that you'd solve for is the velocity. And that would be the maximum allowable velocity to avoid the shear stress going above what the geotechnical analysis says can be tolerated. And so just as an example or an illustration of that, if we know from an analysis that a certain soil has a maximum tractive force, meaning that it can hold itself together under 10 newtons per square meter, and we want to find the maximum velocity that's allowable, the thing that we can do is rearrange the equation to solve for the hydraulic radius. And it's a function of the shear stress, the unit weight of the water, and the channel slope. So for the 10 newtons per square meter and a unit weight of 9810 newtons per meter cubed and the slope of 0.0015, this channel slope that's mentioned here, what we can find is that the equivalent hydraulic radius is 0.068 meters. So that if we solve that in the Mannings equation, 0.068 meters to the 2/3 power, and the slope 0.15 to the 1/2 power, then the maximum velocity in this case that should be allowed to go through the stream is 1.02 meters per second. Based on the geotechnical analysis, any velocity, any water velocity that's greater than that is going to exert a greater shear stress and could cause the stream to scour.
I think it's 0.68. 0.068.
Let's see, 10.
Unless it's not supposed to be 0.0015, I think it's 0.015.
Oh, you're right. Thanks for catching that. I wrote an extra 0 here for the slope because we've got a slope of 1.5%. All right, thank you. So it should be 0.015. You're absolutely right. Okay. So then that gives us 0.068 and the velocity of 1 meter per second. Thanks for catching. There are some things that a hydraulic designer can change, and other things that a hydraulic designer can't change. So let's say that you have a stream coming down out of the mountains, and it's going between 2 points. There's some elevation difference, delta Z, between the 2 points. And if the stream is just straight and it has some length L, we know that the slope is delta Z divided by the length of the stream L. What will increase the velocity of a channel, for one thing, is if it's got a very steep slope. And so if any of you have been skiing before, you know the way to reduce the slope, if you're going down a hill, is to meander back and forth. And so a meandering stream, if you have it increase the length, because now the length of the meandering stream is going to be larger. The delta Z is the same between 0.1 and 0.2, but effectively you can reduce the slope by increasing the channel length. So that would be one way to avoid a maximum velocity that's too high, is to simply change the slope. Another issue is that you could change the material. It may be that what's naturally there has a cohesive strength of only 10 newtons per square meter, but a channel could be reinforced with crushed concrete, something called riprap, where not only are you going to be increasing the end value because it's more rough and that'll slow down the flow, but the tractive force of riprap is probably much larger than the natural soil that would ordinarily just be there under traditional conditions. Okay. So channel design is something that we'll spend more time in the future, but just to give you a sense for some of the parameters the hydraulic design could take into account. Okay, the last thing that the book mentions is a couple of formulas for estimating velocity distribution. And this velocity distribution formula here takes into account something called the von Karman constant, and it's a logarithmic function that relates the velocity for a channel depth as a function of a certain distance from the bottom of the channel relative to the overall depth of flow D. And so it's showing that the velocity is 100% of its velocity for a channel of, this is 0.5%. If you had a 0.5% channel, then graphing the velocity distribution equation, and then for a steeper channel, you can see that it's going to have a more pronounced front where the velocity is higher up at the top than it is down beneath. Average velocities are sometimes estimated by finding the velocity 40% of the depth. So if you have a channel that is 2.5 meters deep and you go 40% up from the bottom, that may be equal to the average velocity, or averaging 20% from the bottom and 80% from the bottom, that the velocities that are at either of those locations. That sometimes when you're taking physical measurements of velocity and want to estimate the average for the stream, because there's a velocity profile, even when there's turbulent conditions, there will be a pretty pronounced velocity profile. So I don't think you'll actually solve any homework problems that ask you to calculate this velocity distribution, but it's important to note that it's just a mathematical approximation of that velocity front. So that's all for today. If we just take a look at these announcements one last time, what you should be working on is updating your load estimates. If you'd like to stop by and double check flow rates with me, feel free. Just what I'd recommend is just take a second look at the things that I have indicated as too high or too low, and check with other students and see what their assumptions were compared to yours. But really, the optimization is what you should be working on to have that ready for Friday. So I will see you on Wednesday.